In this video, we'll talk about Amazon's newly announced VPC Route Server. We'll start with the problem it is solving, explain the solution, and walk through how to configure it. Let us begin with the problem this feature addresses. Imagine you have networking or security virtual appliances inside the VPC, such as firewalls or routers. From the VPC router's perspective, you can only set one next hop per destination. So let's say I configure a static route pointing to R1. What happens if R1 goes down? To solve this, users usually rely on vendor-specific solutions or custom scripts that monitor appliance health and then manually switch to the healthy instances. Some use gateway load balancer, but that only works if your network appliance supports Geneve. There is another problem too. How do you sync the routes learned by your NVA, your network virtual appliances, with the VPC route tables? These appliances often run BGP, which means route learning is dynamic. Take, for example, the prefix 10.2.100.0/24. How do we ensure the VPC route tables automatically track these dynamic prefixes and reflect the updates from appliances like R1 and R2? These two challenges, the redundancy and dynamic route synchronization, are exactly what the new Amazon VPC Route Server is designed to solve. The Amazon VPC Route Server is essentially a BGP speaker that is associated with a single VPC. You can think of endpoints as interfaces of the route server. They live in your VPC subnets and form BGP peering with your virtual appliances. AWS recommends creating 2 endpoints per subnet for high availability. Here's how to deploy a route server in your VPC. You first start by creating the VPC route server. You associate it with your VPC. Again, remember that a VPC route server can only be associated with a single VPC. Next, you create one or more endpoints. Think of those as interfaces of the VPC route server. Next, you choose which VPC route tables you want to propagate the routes to. That is, the route tables that will receive updates from the route server. Finally, establish BGP peering between the route server and your appliances. Now let us look at our lab scenario. We have VPC A, which contains 2 routers, R1 and R2. A route server is associated with this VPC and has 2 endpoints, one in each AZ. Note, for best practice, you would want to have 2 endpoints per AZ, but for this demo, 1 per AZ is fine. We simulate a remote location using VPC B, which has R3. I'm using GRE tunnels here, but IPsec would work similarly. R3 in VPC B forms GRE tunnels to both R1 and R2, and BGP is running over these GRE tunnels. We will use workload A in VPC A and workload B in VPC B to test connectivity. This diagram clearly shows the GRE tunnels from R3 to both R1 and R2 with BGP routing running over the tunnels. In this diagram, let's focus on the prefix 10.2.100.0, which sits behind R3. R3 advertises this prefix to R1 and R2 via eBGP. R1 and R2 then share the prefix with the route server through BGP peering, R1 and R2 via their local endpoints. Now, the route server has 2 paths to reach the prefix 10.2.100.0 in its RIB, the routing information base. It runs best path selection, and let's say R1 wins. That path gets installed in the FIB, which is the forwarding information base. The route server then injects the best route into the VPC route tables that have been configured for propagation. This means the VPC route table now stays in sync with dynamic routes from your appliances like R1 and R2. A major milestone for VPC networking. Now that we have discussed route propagation, let us talk about high availability. Even if both R1 and R2 advertise the same prefix, only one is chosen as the best path and gets installed in the fib. But all valid paths stay in the RIB, again, which is the routing information base. If R1 fails, the route server detects it either through BGP keep alives or BFD, and then removes R1's path from the RIB. The next best path via R2 is installed in the fib and gets propagated to the VPC route table. This is how high availability is achieved with the Amazon VPC Route Server. Now let us look at how some of these constructs are configured from our lab scenario. We have created the route server and assigned it an autonomous system number. The SNS topic can be used to enable notifications for BGP state changes detected by BFD or BGP keep alives. There's also a persist routes setting which, when enabled, can keep the BGP learned routes in the Amazon's route server RIB even if BGP peering goes down for a particular period. You can configure how long to keep those routes. If persist is disabled, the routes will be removed as soon as the BGP peering is down. Next, we associate the route server with a VPC. Remember that it can be only a single VPC, and specify which route tables it will propagate to. Then we create two endpoints in our lab, one in AZA where R1 lives and one in AZB where R2 lives. Each endpoint appears as an elastic network interface, an ENI, in a subnet. From the router's perspective, R1 and R2, the BGP peer IP is the ENI's IP address. We configure BGP peering from the route server side with each of R1 and R2 specifying the peer IP, the peer ASN, the endpoint or interface for that peering, and finally, we look at the BGP status to verify that it is up or down. Now, let us look at the route 10.2.100.0/24. R1 and R2 advertise this route to the route server. So we see two entries in the RIB, the routing information base, but only one, the best path, is installed in the fib, which is the forwarding information base. In this case, I influenced the path to prefer R1 over R2 by ensuring R2 prepends its AS path. So the final VPC route points to an ENI that belongs to R1, proving that the best path is through R1. In this final part of the lab, we validate high availability by causing R1 to go down. We run a ping from workload A in VPC A to workload B in VPC B. As proven before, this goes through R1. Now, we turn off the instance R1. We can see a brief ICMP drop and traffic automatically reroutes to R2. We also look at the routing table. We can now see that the next hop is R2 and the AS path is longer as was our initial intention. Finally, we check the VPC route table. We confirm that the route now points to the ENI of R2, proving that failover worked correctly. So that is the Amazon VPC Route Server, a powerful way to enable dynamic routing, improve resiliency, and synchronize fabric routes into your VPC routing. I hope you find this useful. Thank you.